This is Algebraic Reasoning, Chapter 3.1, exercises 13 through 20. This exercise set has to do with determining inverses of functions. It is a follow-up to the one on problems 1 through 12. I'm going to do 13 and 14 and 17 and 19, I believe, in this video lesson. Use the equation and graph below to answer questions 13 and 14. And we have generate the graph of the inverse of the cubic function. Like I did on the prior video, I'm going to do similarly here. Okay, I'm going to go ahead and transpose some of these points for the inverse. So I'll put x and y for the inverse. We're going to take this point down here below -3, comma -4, and make that -4, -3. We're going to take this point -2, comma -3.5 and make that -3.5, comma -2. We're going to take this x-intercept here of -1, comma 0 and make that the y-intercept of 0, comma -1. We're going to take this y-intercept here of 0, comma 9.5 and make that the x-intercept of 9.5, comma 0. And so those are the points that we're going to transcribe and get there from an inverse function. So -4, -3, so go to -4, -4, and -1, 2, 3, that is. That'll be it right there. We're going to have -3.5, -2 will be right here. We will have 0, comma -1 will be right here. The y-intercept, and finally oops, I got that wrong here. It's going to be 0, -1. There we go. Then we have 9.5, comma 0. We have to kind of extrapolate. So 6, 7, 8, 9, about 9.50. So this point over here. So what that is going to look like is something like this. Let me put them here. Like this. Yeah, and so you have an inverse function right there, and inverse function reflects about the line y equals x. So it'll look something like this. And the aspect is a little wrong since your x and y's don't have equal value here on the scale of the graph, but I think you hope you can get the basic idea of what an inverse function looks like. 14, determine if the x-intercept and y-intercept, original function, and, well, I looked at the wording, and this word if isn't supposed to be, so determine the x-intercepts and y-intercepts of the original function, the x-intercepts and y-intercepts of the inverse function. So here you have, I'm going to just color code them. For the original function, we have an x-intercept here in green, and a y-intercept up here in green. And for the inverse function, we have a y-intercept here and an x-intercept up here. And you can see, I hope, where the inverses, these intercepts correspond with each other. X's become y's and y's become x's. Now I'm going to leave it to the viewer to work out a inverse function here. It looks like an exponential function. Same process. You're going to have something that looks like this. Anyway, you'd have to do it, just switch x and y's and draw the curve. And again, it's going to be determine, not determine if, determine the x-intercepts and y-intercepts of the original function and the x-intercepts and y-intercepts. Okay, for questions 17 through 20, generate f-1 of x. In this f-1 of x, that is called inverse function notation. What it is, this is algebraically or analytically, and there's a four-step process to determining inverses from functions. You have f of x, so step one, change f of x to y. So I'm going to do that with this first function here, f of x. So I'm going to say change that to y equals 3x minus 2. So that's step one. Yeah, circle that. Step two, it's x and y's switch places. So here we go. I'm going to put step two over here, and the switching places is going to be, instead of y equals 3x minus 2, we're going to have x equals 3y minus 2. Okay, now step three is solve for y. And step three is usually our biggest step because you might have quite a few steps to have to solve for y. So I'm going to solve for y here, and I'm going to rewrite this equation as 3y minus 2 equals x. Why am I doing that? I want to have the variable I'm solving for, or the unknown I'm solving for, on the left side. So now going through the solving process, if we add 2 to both sides of this equation, cancel out, we have 3y equals x plus 2. Now we're going to solve for y by just dividing both sides of this equation by 3, and we have y equals, and then x divided by 3 is 1/3 x, and 2 divided by 3 is going to be 2/3. And then step 4, last step, is change y to our inverse function notation of f-1 of x. So we come over here, step 4, we have f-1, and this -1 looks like -1 power, but it's not. It's what the convention is for inverse function notation. And so there it is, the four-step process. And if you graphed each of these functions, the original one up here, this f of x up here, and the one down below, you would see that inverse function pattern where the x becomes y's x is x-intercept of one or y-intercept of the other, and so forth. Next, I'm going to do problem 19. I'm going to do the four-step process as I did before. So step 1 is we're going to say y equals -2 times quantity 3x plus 1 squared. Next, x and y switch places. So I'm going to just put step 1. Step 2, okay. We have x equals -2 times quantity 3y plus 1 squared. Okay. Next, 3. Solve for y. So I'm going to put negative 2 times quantity 3y plus 1 squared equals x. Now the first thing I'm going to do to get rid of this squared, I'm just going to rewrite this down here to make it more apparent for demonstrative purposes. Squared equals x. So to get rid of this squared, I'm going to take the square root of both sides, but before that, I'm going to divide by negative 2. So we have quantity 3y plus 1 squared equals, I'm going to put the negative sign up here, negative x over 2. Next, we're going to get rid of that square root symbol get rid of that squared by taking the square root of both sides. Okay, so I'm going to just come up here to give myself room to work on the upper right. So we have the square root of squared, they cancel out, and we have 3y plus 1 is equal to square root of negative x over 2. Now, is this the proper algebraic step? Well, when we take the square root of a squared, the other side we're going to have plus or minus when we solve using the square root. So we have plus or minus square root of negative x over 2. And I think we can take that negative sign outside too, but I'll just leave it in there. It really doesn't matter. So next, we're going to continue to solve by subtracting 1 from both sides. So 1 minus 1 cancel on the left. So we have 3y is equal to plus or minus the square root of negative x over 2 minus 1. And what I'm going to do is just bifurcate at this point. And this is usually it's more complicated. Okay. So what I'm going to do is work two equations at the same time. We have it's plus or minus. So I have square root of negative x over 2 minus 1. And then we have 3y is equal to negative square root of x over 2 minus 1. So you have two equations you're solving for. Last step, divide by 3. And that will cancel. We got to do the same thing on the other side. So we have y equals square root of negative x over 2 minus 1 and divide that by 3. And also we have y equals negative square root of negative x over 2 minus 1 and divide that by 3. And the last step, we're going to take the inverse function notation. So f negative 1 of x is equal to square root of negative x over 2 minus 1 over 3. And also f negative 1 of x is equal to square root of negative x over 2 minus 1 over 3. Now, why do we have to separate these into two functions to get original? Because this original, number 19, is going to be a downward opening parabola. And I don't know exactly what it looks like. So the parabola is going to be opening 3x plus 1, it's going to go left, so the parabola is going to be opening down like that. And its inverse is going to be something like, okay, that's going to be Y-intercept. It can be something like this. Okay, one function here, another function here. So the red one, you see this red one here is not a single function because that would fail the vertical line test. So we have two functions we need to create to take the inverse of this one. There's some complexity involved here. Good luck, and thanks for viewing.